Okay, let's talk about N wells. Next, we are going to start doing that N well layout to replace the deck. So keep in mind, the lab yesterday we did a R2R deck, but it's a schematic. So after doing all this layout, you probably have a concept about all these layers. Remember, in electric VLSI, it's an open source tool, but also for Cadence and other tools, you have schematic view and icon view. So the icon view is a symbol that you can directly use for other design. You can directly drag and put into somewhere else for a bigger design. So it's a cell view. A cell view includes schematic view, icon view, and a layout view. We haven't done a layout yet. So next week on Thursday, we're going to do our first layout, which is just a resistor string, use the R2R deck. So they have to match. The schematic and the layout have to match in order to pass LVS, which is layout versus schematic. So there will be two major checks, DRC and LVS. So DRC is design rule check, LVS layout versus schematic. So layout will be the physical design. Eventually, these layout drawings will be converted into printing on the mask. Oh, I didn't bring my PCB. It's a very similar concept. I did the PCB fabrication at home for my senior son. That was how many years ago? Oh my goodness, I'm so old. 18 years ago. My goodness. Right. Let's talk about N wells. So first, N well is an N-type semiconductor material. So we have to talk about what is the N-type semiconductor. Really quick, just one page, since a lot of you have taken analog or semiconductor engineering, that class by Dr. Jessing. N-type. That's a silicon atom. Silicon. And you dope that silicon material with a phosphorus. Material, and eventually, because this one has 5 free electrons on the outer layer, right? So eventually, 4 of them will form 4 covalent bonds with the silicon atoms. Okay, but there will be one extra one over here. This is forming a free electron. So that's why it's N-type, because N represents negative, I think. So eventually it's N-type because there's one more free electron. Okay. For P-type, so you are doping the silicon material with the boron. Did I spell this right? So there will be 1, 2, 3, 4 free electrons to forming all these covalent bonds. But the thing is, the boron atom only has 3 free electrons to form all these covalent bonds. So eventually there will be a hole left over here without having an electron to fill it up. So eventually it's forming it's called P-type because this is positive, it's plus, right? So that's why it's called P-type material. Am I right? N-type, P-type.
You're right.
Yes. And then if you put a P-type and N-type material together to form a p-n junction, so P-type has free holes, and N-type forms free electrons. If you put them together to form a p-n junction, right? It's the p-n junction. So what's going to happen, because there's a concentration gradient, right? Concentration gradient. So it results in a migration of these free electrons and free holes to move to each other. So eventually, this one comes here and combine with all these holes. Is that interesting? Why whenever after these electrons combine with all these holes, it becomes negative charged? Why is that? Can you recall that from analog or semiconductor? How many of you have taken analog? 3? Like 1, 2, 4. A lot of you guys. And also semiconductor this semester? A couple of you guys, yeah. Why? It should neutralize it, right?
There's fixed charges in there, and when the holes move this way, it's going to be negatively charged.
Yeah, but why? Because these ones come over here, fill up the holes, should be neutralized. Once eventually it becomes the electron. So it's a little bit confusing, right? Physics.
Because they get filled up, right? Holes, and so they just kind of shift.
Yeah. Sounds like it's neutralized, but eventually it's negatively charged. So the way to explain that is, because I cannot get into the micro world to exactly see what's really going on, but the thing is, so silicon, if I give you a piece of silicon, is it neutral or something like negative or positive charged? Just a piece of silicon, nothing, okay? It's neutral, right? A piece of silicon is neutral, and a piece of phosphorus is also neutral. And if you mix these two things, even though they are free electrons, but actually it's still neutral. You know what I mean? So if you mix the phosphorus or dope phosphorus with the silicon material to form an N-type semiconductor, it is still neutral. Okay? So that's why if you put them together for a neutral piece of semiconductor material, has more electrons inside, eventually it becomes negatively charged. It's a bit confusing, but that's how that works, right? It's the same concept for the other side. You have a neutral piece of material, which is silicon, and neutral material, which is boron, and you mix them together, should still be neutral because both are neutral at the very beginning. Even though they form a p-type, there are free holes, but still neutral. Just keep that in mind, still neutral. So that's why whenever there's a diffusion, because of the concentration gradient, so the holes will migrate to the right, but actually it's the flow. Electrons going away left holes in there. So, but we just explained the way that the holes are also going to the right. Actually, holes are not moving, right? Just keep that in mind. So we just imagine the holes are moving to the right to form a positive charged field. So eventually, these two pieces are forming an electric field because plus and minus, right? So electric field is pointing to the left. All right. So we need to know that because it's forming a capacitance between these two layers. You got two. There's a thickness in between them. Let's call it T, whatever. Just call it T. So this thickness and these two layers of materials will form a junction capacitor, CJ. It's called junction capacitor. So you know that when you are charging and discharging an LED, is that mine? No. Okay, if you are charging and discharging the LED, it's not just a resistor model. If you model it, it should be a cap and a resistor for this diode, right? Because it has a junction capacitance built in the pin junction. Okay. So my quick question for you guys is, if I like here's the pin junction. If I do this, plus minus, okay, plus minus. Is this called forward biased or reverse biased? It's forward biased because plus to plus, minus to minus, so it's called forward biased. So it results in a thinner junction capacitor or thicker junction capacitor. So here, the depletion, so this region is called depletion region.
Thinner,
Why?
because the depletion region shrinks.
Yeah, so you can imagine that if you have a anode here, cathode here, so what's happening is it's canceling all these free electrons, so eventually it's getting thinner. So we are getting a thinner depletion region. Cj goes up or goes down. So let's say this, okay? T, which is the thickness, if it's getting thinner, Cj goes up or goes down, and why? So C equals what? Epsilon T over, no, A over T. So how that works? So whenever this getting thinner and thinner, so the electrons can get through, right? Can tunnel through this depletion region. That's how that works. So that's why you need a threshold. So whenever you are looking at the IV curve should have V here and I here for the diode. Okay? So whenever the voltage passes a certain threshold voltage, the current starts going up. So for silicon material, usually this is like 0.6 to 0.7 volts, right? So that is the built-in potential of this, like formed by this electric field. So you have to reverse it in order to, passes that current through that diode. So eventually, this getting thinner, because this is getting thinner, right? T is getting smaller, so capacitance will be bigger. So thinner depletion region will give you a bigger junction capacitance. That's the conclusion here. And the other way around, if you look at the pin junction and you reversely bias it, because it's P to N, N to P, it's reverse biased. So T will be thicker, so the depletion region will be thicker, so Cj will be smaller. Okay? Any question on this? So when you do a forward biasing, you see this depletion region here, it's forming an electric field pointing to the left. So it's plus minus, right? So that's why when you are trying to flow current through it, which means you are doing a forward biasing, you can see these electric fields are opposite to each other. So that is why this one has to overcome this building voltage first in order to run current through the diode. And that's why the diodes usually have a threshold voltage here. You have to pass that building potential in order to run current through the diode. Okay, so we need to know that is because for a silicon wafer, if you look at the silicon wafer from the side, where it's a cross-sectional view, usually it's a P-type substrate. P-sub, we call it P-sub. It's a P-type. P-type substrate, and if there's the N-well material being doped into the P-sub material, it's a silicon wafer, and it's being doped slightly with a P-type material, so it's called a P-sub, P-type substrate, or P-sub, and that's the wafer body itself. Sometimes we call this body. It's a really weird term, body, and we dope an N-type material into the P-sub to form an N-well. It's an N-type material being doped into that P-substrate and form a well, so we call it N-well. But is it really a well? No, there's no well. It's just an N-type material being put into the P-substrate. So if you're looking from the side, it looks like this. even though the wafer is very thin. But if you can put it underneath the microscope, you can see it will be an well and substrate like this. It's just a wafer's thickness, super thin. Right? If you look from the top, it's just basically a wafer. You have a well in here. Okay. And here's the P-sub. Depending on your application, you can dope it in all different types of shapes. But now we're just looking at the side, from the side. So it's like a pie, right? Apple pie. You cut it in the middle so you can see from the side. So it has a P-sub, has an N-well like this. So you can tell it's forming a pin junction, even though it's not exactly the same as the diode, P and N, right? It's forming a pin junction. So there's a parasitic diode over here. You can treat this as diode. So if there's a pin junction, there will be a layer in the middle. And what's the name of the layer? We just talked about. You got a pin junction, there will be something in the middle. Yeah, depletion region, right? Depletion region. So there will be a depletion zone here. Okay? And so what is the thickness? Where is the thickness of the N well? It's basically over here. So that's the thickness of the N well. All right? We want to know that is because you have to calculate the resistance of the N well, since a lot of times we're using the N well to form resistors. So that will be lab 2 next week on Thursday. So we're using N wells to form resistors. The N well has a certain resistivity inside, and which is given depending on the foundry's doping concentration. So we know a certain resistance of this material. And the thickness is not changing because the foundry's manufacturing procedure is going to dope a certain thickness or depth into the wafer. It's not changing. So it's a constant. So what you can change is basically something you are looking from the top. So this is the top view, and this is the side view. All right, so thickness is not changing. So the only dimensions that I can modify will be the length and width from the top. So when you are drawing layout in electrical VLSI, you're actually drawing the width and length. There's nothing going into the monitor. It's going to break the monitor. So you cannot draw anything into the monitor. There's nothing going into the monitor. So anything going into the monitor will be the thickness. It's a depth dimension because you are looking from the top. Does that make sense? Okay, so you are drawing everything from the top view. You are looking from the top. Okay, the thickness is already defined by the manufacturing process. It's not being changed. So in that case, for example, I'm drawing a rod of an N-well. It probably looks like this. Like this, okay? So we take this out, take this N-well out. It probably looks like this. So what is this dimension? Depth, right? Thickness, T. What is this dimension? Or here, it's the same, right? Let's call it width. And this one here will be the length, right? Okay, so if we are using this kind of rod as a resistor, you need to know that R equals what? R equals rho, which is resistivity, times L over T times width. Ohms. So T times W will be the area here. Okay, area, and times length will be the volume, and times resistivity will be the resistance. Okay, so that's the definition of the resistance of a certain material. It could be other materials, but the resistivity parameter here will be changed, right? So resistance equals resistivity times L over A. A is the cross-section area. So this is A. Okay. So if we are looking from the top, when we are doing the layout, we're just drawing a square or box because there's no dimension for the depth. So we are not laying out the depth. So when we are looking at the top, there's a critical parameter that we should use for this technology we are using for electric VLSI, which is called sheet resistance. Okay, and that is 800 ohms per square. (800 ohms per square). That means if we draw a square, and this piece of unwell as a square, and the resistance, if we draw a current, flow a current through it, and that will be 800 ohms. So my quick question is, if you increase the area, for example, a square like this, or a square like this, do they have the same resistance? Why and why not? Why or why not? So if I draw this little piece of unwell in electric VLSI, and I draw flow a current through it, or like this guy, I flow current through it, do they have the same resistance? They have the same resistance. It should, because it's called sheet resistance. It's 800 ohms per square. So even though it's a different square, but it's still a square, right? So it's 800 ohms per square. Same resistance. So in that case, should you use bigger squares or smaller squares? Smaller squares. So to save more space, right, on the chip, you can integrate more circuits onto the chip. So use small squares. So you want to choose the minimum width over here to be the minimum width you can do for an unwell. So whatever the foundry can fabricate on the chip for the unwell, you just use that width. It should be the minimum width. And then you start extending it to another side, right? Until you reach that goal for the resistance. So let's look at one example over here. Calculate the resistance. Here's the unwell. Okay, and this dimension is 10. I'm just telling you it's a 10, but there's no unit. Keep that in mind. In your electric VLSI design, we are using a technology called C5. It's just the name of the technology, and that's a 500 nanometer technology. It's about 45 years old technology. 500 nanometer means the minimum length you can fabricate on the wafer is going to be 500 nanometers, like half micron for one transistor's length. That's awful. So 500 nanometers is the minimum length you can fabricate. However, we are using a rule called lambda rule for the design. What does that mean? Even though it's a very old technology, but it's a very starting point, so we can understand what's really going on, how things evolved, right? So lambda rule, we are using lambda in our design, which is 300 nanometers. So the minimum dimensions for everything will be 2 lambda minimum. And that's interesting, right? Because the minimum length you can fabricate is 500 nanometers. However, you are using 2 lambda, which is 600 nanometers as a minimum. Why? You just want to increase the yield. Okay, so it's more reliable to use 2 lambda as the minimum in that 500 nanometer technology, even though the minimum they can fabricate is 500 nanometers, but the chance to fail some of the transistors is high, right? So that's why I want to keep using 2 lambda just to make sure that all these dimensions are manufacturable and reliable. Okay, so 2 lambda is a rule over here, or a lambda rule, and we usually use 2 lambda as a minimum dimension for the transistors. But not always everywhere, because lambda is the minimum unit. There won't be like 0.5 lambda, but it's usually larger than lambda. So there will be several other rules defining the space between metal 1s, metal 2s, between metal 1, 2, poly, all these kind of things, and we'll talk about later. But now we need to know that lambda is 300 nanometers in our design. 1 lambda. So for this N well, if I tell you it's 10, that means 10 lambda. So if I tell you it's 10, that means it's going to be 10 times 300 nanometers. So that would be 3 micron. But we don't have to worry about that since we're only calculating the number of squares of this N well resistor. So L here equals what? 30 lambda. What is the resistance of this N well? What's the resistance? 2.4K. Sheet resistance R square times L over W, which is 800 ohms, times 30 over 10, which is 2.4K ohms. Okay. So knowing this will be very beneficial because you'll know that a N-well resistor is causing time delays. RC delay through let's draw this circuit here. This is substrate from the side and input so that's how you model it. It's a piece of N-well. Let's draw a substrate over here so you'll know it's in the substrate. It's an N-type well. It's N-well. Input, output. So what is the capacitance I'm modeling here? So the resistor you can understand because it's a piece of N-well and we divide it into its sheet resistance. So that's R square. So what is the capacitance over here? What's the capacitance over here? Why do we model capacitor for the N-well? What is it for? The reason we model is because it has capacitors, parasitic capacitors over here as an N-well. So you know that whenever you are driving the N-well, it's not just a pure resistor to cause time delays. Okay, that's why we model it. So what is the capacitance over here? It's the junction capacitance we just talked about, right? This is the pin junction. The pin junctions, there's a certain layer here, and between these two boundaries, it's forming a junction capacitance. So the pin junction is going to form a capacitor, which is called junction capacitance. And that's why if you dope an N-type, how do you dope it? I mean, a lot of guys learn it in analog, right? Dr. Jessen's, that's his expertise. So how do you dope it into the silicon wafer? High pressure, high temperature, vacuum, all these kind of conditions, and then you just inject that type of material into the chamber, and eventually it's gonna diffuse into the substrate, into the silicon substrate. That's how it gets into the substrate. So dope that material into the substrate to form a pin junction. Eventually, it's forming all these junction capacitance. That's how that works. So in that case, you got the resistance done well, and also the junction capacitance eventually is forming this RC circuit. So you should know that when you are calculating the timing, there will be a time delay. So how do we calculate it? How to calculate it? So we can model these ones because these are called R squares, and these are called C squares. It's a unit capacitance for each piece. Another set question here. So for capacitance, if I have a little square and a bigger square, do they have the same capacitance? Definitely not. But resistance, they do have the same resistance, but they don't have the same capacitance. Why? Because capacitance equals what? Epsilon A over T. And that's the thickness of the dielectric material in between the two plates of the cap. So that's T, right? That's T. And A is the area. So thickness is not being changed. The T is not being changed because of the manufacturing standard procedure, right? So it's not being changed. However, you have a bigger square, have a bigger A. So bigger A will give you a bigger cap. So we're just using one square of the capacitor over here. We divide it into multiple squares. This is one square of the capacitor over here. Just modeling this in that way, okay? So TD, if we label this as, this is input, and label this point as A, B, C. Let's draw another more generic circuit here, because there will be more than this. For example, there are a lot, not just 3. And here's V out. Here's V in. Okay? So I label this point as A, B, C, like this. So T time delay A to point A, from here to point A, will be 0.7 R square times C square. So it's not the standard form of the RC circuit only has one resistor and one capacitor in series, so you can easily calculate the time delay from here to here, which is going to be 0.7 RC. However, you have so many other ones, like repeating in that way. So before moving forward, let's think about it. How do we calculate it? If I don't show you this example, but do you have any other ideas? What are the ways to calculate the time delay from V in to V out? Superposition works, yeah. Yeah, that's what we are going to do over here actually. But you can imagine, so all these time delays, all these capacitors can be modeled in a way that, it's very close to the result that you add all the capacitors together and add all the resistors together. So it's going to be the overall R and overall C. So it's going to be a 0.7 times overall R times overall C. But now let's derive it first. TDA equals this from here to A, right? There will be a time delay, which is this. From here to B, there will be another time delay. And what is it? TDB. So we are separating all these caps because every single cap is a bucket. You can imagine all the capacitors are buckets, and you are using water hoses to fill up the buckets with water. Okay, so these are just individual buckets hanging there, and with a major hose with water in it, and these are just the hose limitations of the water flow to limit the water flow in it. But these are individual buckets holding a certain amount of water. Okay, so now let's just fill up the first water bucket. So that will be 0.7 RC. Okay, if we fill up the second bucket, it's going to be 0.72 R square C. TDC will be 0.7 times 3 R square because of this. So keep going. we can finish all these time delay equations. TD V out, for example, equals what? 0.7 times. If we define the number of R squares to be L, which is the length, okay, L, the number of R squares to be L, 1, 2, 3, L, okay, that will be L times R square times C square. So if you add all these time delays together, will be the overall time delay. Superposition, yes, that's the concept over here. So overall time delay equals TDA plus TDB plus TDC plus TDL or TDV out, and that equals 0.7 R square. Factor out R square and C square and 0.7. And it becomes 1 plus 2 plus 3 plus L. And this one equals L times 1 plus L, if L is large enough, divided by 2. So that's the equation for this addition here. If L is big enough, or if L is a pretty large number, L is pretty much equals to L plus 1. Doesn't matter. If 1,000 equals, is pretty much equals 1,001, right? So whenever it's large enough, L is almost L plus 1. So eventually this becomes 0.7 R square times C square times L square over 2, and which is 0.75 R square times C square times L square. Okay, here's the conclusion. So that's the overall time delay for an N-well resistor. So from one terminal to the other terminal, it's going to cause this much time delay. Okay? Let's look at one example here. There's an N-well. The W is, the width is 10 lambda. L is 500. L is 500. R, the resistance, overall resistance is 250 k ohms. It's given. And a 10 by 10 capacitor is 5 femtofarads. It's given. Okay, it's given. 10 by 10 capacitor of the N-well is 5 femtofarads. What is TD? Time delay from one terminal to the other terminal, TD. What's the first thing to calculate? Just look at this equation here, right?
R squared and C squared.
Yeah, so TD equals 0.7535 times R square. What is R square? What is R square here? how many squares do you have? So R squared equals what for this example? R squared equals what? Overall resistance will be 250 k ohms, and you have 50 squares, right? So every square will be 50 k ohms divided by 500 over 10. So that's the number of squares you have. Eventually, every square is going to be 5 kilo ohms, right? Okay, so this becomes this times 5,000 times C squared, which is given 5 femtofarads. So femto is 10 to the negative 15th, right? And times L. So keep in mind, L is not the real length. L is the number of squares. So how many squares do you have? Let me write it down here. So L say 50 L's. Okay, that's the equation to calculate it. So what's the unit for this? Just seconds, right? Seconds. I did the calculation. Eventually, I think the result is about 22 nanoseconds time delay. Any questions on this? Before we're moving forward, I think we should do our quiz right now. When you are doing that DAC calculation, make sure that you show all these equivalent circuits to receive credits. And also all these intermediate results as well, right? If you just throw a final result